Welcome in to End Alzheimer's. I'm with Dr. KARL HERRUP with us today. Dr. KARL HERRUP is a professor of neurobiology and investigator in the Alzheimer's Disease Research Center at the University of Pittsburgh School of Medicine. He's also adjunct professor of life science at the Hong Kong University of Science and Technology, where he was formerly head of life sciences. He has seven different grants from the National Institute of Health, amongst other things, amongst many other things, each peer-reviewed. And I'll stop there. But we're extremely lucky to have Dr. KARL HERRUP with us today. We're going to talk some about his new book, How Not to Investigate a Disease. And we're also going to talk a little bit about Cassava Sciences. This is not sponsored by Cassava Sciences. They have nothing to do with this. And with that, let's get started. Dr. HERRUP, how are you?
I'm fine, thank you. Glad to be here.
Excellent, excellent, super. I just wanted to do a technical check real quick, but I think we're all set here. Yeah, I think we're all set. Okay, let's get started. So, Dr. HERRUP, can you tell us a bit about yourself?
Sure. I've been in science for more years than I like to count, but I entered the Alzheimer field back in 1992. So while I wasn't there in the beginning, I certainly have gone through the maturation of the field over the course of those many, many years. And I've professionally always been in academia, always been a basic scientist. And my personal interests are in the basic science of Alzheimer's disease, the cell biology, the biochemistry. But I've had a long and intimate relationship with the clinical aspects as well. So I believe that the only way to really think about this disease is to think about it in its broadest possible terms. So from the molecule all the way to the individual person with the disease.
Awesome. So terrific. Oh, that's right up the alley of what we'd love to hear about. What we would love to hear about here on this channel, and what the audience wants to hear about. So thanks so much for making time to come and visit us. Okay, and then can you tell us how this is something you wrote about in your latest book? Can you tell us how the Alzheimer's field became dominated by the amyloid cascade hypothesis?
Yeah, so I spend a lot of time in the book actually diving into that very question. I think, and I point this out in the book, that it began with some very good science, and I talk about the discoveries that sort of revolutionized the field and in many ways misled us because of their success. But in the beginning, the amyloid cascade hypothesis was extremely thoughtful and very forward-looking. What happened over time, though, and this is what's so frustrating to me as a basic scientist in the field, what happened over time is that we stopped listening to our data. And so the two things happened simultaneously. The first is that the other ideas were suppressed, so that if the classic statement that I refer to again and again in the book is the admonition I got from one of the external scientific advisors of a review group when I was doing Case Western in Cleveland. And the basic was explicitly, if you're not studying amyloid, you're not studying Alzheimer's. That is fine if it's a statement of hypothesis, but what came along with that was the very clear statement that if you're not studying amyloid, you're not studying Alzheimer's. And the partner of that is that if you are studying something else, you're wasting your time. And that led to a suppression of other approaches that I think haunts us to this day.
Yeah.
Combined with that was a consistent expansion, I call it inflation, of the definition of Alzheimer's disease. So originally, let's say back in the middle of last century, Alzheimer's disease was a very rare form of what we would call presenile dementia, so early onset dementia. And it was only through the concerted political efforts of a group of people that the definition was expanded to cover more and more of all late onset dementia. And those two forces acting together, the expansion of the definition and the suppression of other approaches to study dementia, led almost inexorably to the dominance of the Alzheimer's cascade hypothesis in our field.
Were the political forces the same ones that were pushing the amyloid hypothesis? The political forces that pushed for the expansion of the Alzheimer's umbrella?
The people involved were different, but they were certainly playing off each other, to be sure.
Who were the political people? What was that about?
Yeah, so that I would say the one group would be a group of physician scientists who felt that they were really onto something and that we were like this close to solving Alzheimer's disease as long as we just could get rid of amyloid. And the expansion of the definition, however, was driven, I think, in large part by the politics of the NIH, tracing back to the foundation of the National Institute on Aging. The early drivers of that institute felt that they didn't have enough of a case to make to really bring in a lot of federal research dollars. So they struggled to come up with a face of aging that could be something horrible. And they chose Alzheimer's disease. And to make that work, they had to make it something really nasty and malevolent. And they did that in both their writing and in their lobbying. And as a result, the definition got inflated to include not only what we would used to call presenile dementia, but most of what we call senile dementia, which is age-appropriate decline in cognition.
Interesting.
And those two forces acting together were, I think, the crux of the story.
Is there an age? So you talked about an age-appropriate decline in cognition. Is there an age-appropriate behavioral aspect of things? Are people, as they age, is there any natural acting out as far as anger and like in Alzheimer's, you get to the point of biting, like Dr. Harp. Is there any natural as cognition can decline naturally? Is there any bad behavior that comes with natural senility? I
see your question. I would say probably less. I mean, what aging does as our brains age, there is a whole set of natural abilities that are diminished. So our reaction time diminishes, our executive processing diminishes. Behavior less, but it's not. Our behavior certainly does change, and things like apathy and depression, while associated in symptoms of Alzheimer's disease, are nonetheless more common as we get older. But I would really want to stress at this point that while there is a natural decline with aging, there is also a disease process which we can recognize clinically as something that we would call Alzheimer's disease, or let's call it dementia.
Yes.
That is a disease process. It is not just accelerated aging. Something happens to change the biology of our brains and add a second factor on top of the natural loss of capacity.
Brilliant answer. Thank you very much for that full explanation. Thank you. And then, so moving right along. So, what is the difference? So, this is something you talk about in the book. There, that the Biogen's Aduhelm was approved on a surrogate endpoint, a biomarker. It did, in fact, clear amyloid plaques effectively, but whether or not that was good for anything is in question. So so the question is, what's the difference between normal patient benefit endpoints like cognition, for example, and surrogate endpoints in clinical trials before the FDA, specifically between cognition measures and amyloid measures in Alzheimer's? And why have all the existing amyloid-focused approaches sought approval based on surrogate endpoint on reduced amyloid rather than an endpoint of actual cognition improvement?
So that's a great question. And the answer, it will not surprise you, is a complicated one. So what the Aduhelm decision and the FDA's Aduhelm decision indicates is that moving a biomarker, that is affecting a biomarker such as amyloid deposition, can be an extremely useful part of a clinical trial. And the reason for that is that, and it's especially true with a disease like Alzheimer's, where the effect that you're looking for is going to be measured over the course of many, many months, and in fact, years. If you're looking at a full clinical picture, so just what a clinician would see in their office looking at someone. So to have a biomarker, which is to say some physiological or biochemical change that is both reliable and informative, and to track that change instead of the cognition, can be extraordinarily valuable. But, and here's where the controversy around the Aduhelm decision comes into play, that marker has to be reliable and valid. And if that marker is not reliable and valid, then changing it, for better or for worse, becomes irrelevant. And for those of us who are critical of the FDA's decision, that really is the fundamental problem that we've got, which is that you've moved a biomarker. Nobody's questioning that. But what we are questioning is whether that alone is enough to merit approval of a drug for a specific disease, which may or may not, and I hope my colleagues will forgive me, be related to the progress of Alzheimer's disease.
And there's a history of the mechanism of action in medicine. It does not have a history of being important. The medicines were used for thousands of years before anyone knew how they worked. So
Right.
so to to sort of put the cart before the horse there and say to approve it on something that's really irrelevant in the first place. That's not, you don't need to have a proven mechanism of action in the first place. So thank you very much for all that. Thank you.
Mm.
And so following on with all of that, how groundbreaking would it be then for an approval based on cognition as the actual endpoint? How groundbreaking would that be?
I think ironically enough, it in many ways represent a return to the way we used to do clinical trials. And I, right now we are so, I guess, in love with the concept of biomarkers and moving biomarkers. We've lost sight of the fact that all of the cholinesterase inhibitors were approved based on their ability to move the MMSE.
Yeah.
And so, but somehow those markers, which were the gold standard, if you will, back in the day, have been virtually abandoned. And it's sad because, as I say in the book, I don't care if my grandmother has a head full of plaques or her brain is squeaky clean. I just want to be able to play Scrabble with her and have a decent conversation.
Yeah, and then someone else said nobody goes to the doctor because of biomarkers. Is that you?
No, but I wish I had.
Yeah, no, that's right. Nobody, right. So terrific. Thank you very much. Uh, and so now this has been the amyloid cascade hypothesis stunted the field for a long time, but now you are researching a number of ways that Alzheimer's could develop. What are some of the theories besides the amyloid hypothesis?
Right. So I do also in the book spend a lot of time going over these, their strengths and weaknesses, and the way in which research into them has been diminished and held in less repute than studies on amyloid. But and the list is very long. So I in my own well, let me start off by saying that the most important thing that we need to be studying, and I actually devote an entire chapter to this in the book, is aging.
Yeah.
Because young people simply do not get Alzheimer's disease. Even the most aggressive genetic forms of Alzheimer's, which are rare, but even the most aggressive forms don't strike until the 30s. And even that's early there. We're looking at 40s and 50s as early, what's called early onset. Alzheimer's disease, by and large, the sort of demarcation age is about 65 years of age.
Yeah.
Well, how is our brain working beautifully for 65 years and suddenly falls apart and starts to create Alzheimer's? What it says is that there is something about the biology of aging that interacts with the network and functional properties of our brain and just derails them. So we need to put a huge amount of effort into that. And to sort of jump ahead a bit, I do feel that that is one area where we've been straightening up and flying right, because the field of aging has been much more vigorous in the last 5 to 10 years. For Alzheimer's itself, I look, amyloid is there. I can't say it's irrelevant, but it belongs in a much larger biological context. And in that context, I would certainly put inflammation, neuroinflammation, that is to say, the development of inflammatory processes in the brain. I would put the degradation of myelin, which is the wrapping around neuronal axons that helps their transmission to be both healthy and rapid. I would put DNA damage. I would put calcium homeostasis. I would put cellular senescence. The list is quite long. In my own lab, we're focusing on myelin quite intensively, as well as inflammation and DNA damage, and those two are actually related.
Thank you. How do you rate tau tangling?
Oh, thank you. That should have been on my list. I think it's quite important, and it's not unique to Alzheimer's disease, but clearly when it's dysregulated, you have a heightened potential for neurodegenerative problems.
Okay. So you see some tau tangling in aging, but not perhaps the hallmark.
Yes.
Okay, great. And then can I ask, I've recently seen synuclein. So synuclein is said to be a misfolding protein or at least a troublesome protein in Parkinson's. But now I've also seen some things that it's now shown to be play some sort of a role in Alzheimer's as well. Is that, do you have any insight on synuclein and Alzheimer's?
Yes and no. I mean, it's what it's called a comorbidity, which means that it comes along with the clinical diagnosis of Alzheimer's disease. And by the way, it's not just the alpha-synuclein, but also a protein known as TDP43. They have specific lesions. It tends to be associated with other forms of neurodegeneration, including ALS. My view of this is that they're called proteinopathies, where the proteins lose their normal structure and deposit in abnormal ways. That these proteinopathies are both potentially causal, but also potentially symptomatic.
Yeah.
And we would like very much, and there's lots of good data, that losing the ability to keep proteins properly folded is a major problem of aging.
Yeah.
And I think that it goes along with the development of a lot of these neurodegenerative diseases, indeed.
Interesting. Thank you very much. I really appreciate that answer. Thank you very much. Okay, look, I'll keep moving here. I'm throwing in some extra questions along the way. I really appreciate you fielding those as well.
Sure.
So the science behind Alzheimer's disease is not fully understood. How do scientists at the National Institute of Health know that research is promising enough to fund with tax dollars? And how do regulators, scientists at the FDA, know what endpoints of a trial suggest success?
Right. So two very big topics there, NIH being one topic and regulators such as the FDA being a second. The NIH, I spent a chapter in the book discussing the history of Alzheimer's research at the NIH. And one of the things I try and point out is that it got inserted into it's in an odd place at NIH. So the National Institutes of Health are actually a number of different institutes. The two most likely ones where Alzheimer's research could be done would be NINDS, which stands for the National Institute of Neurological Diseases and Stroke, or the National Institute on Aging, or NIA. And you'll remember that I told you that the NIA, when it was founded, grabbed onto Alzheimer's disease as a way of making their institute more attractive for federal research dollars. But if you fast forward to 2022, what we find is that virtually every neurodegenerative disease, be it epilepsy, Huntington's, Parkinson's, ALS, virtually every one of them is studied as a nervous system disease. So it's in NINDS. And the only exception is Alzheimer's disease, which is all by itself in the National Institute of Aging. Now, obviously, there's interaction among them, but structurally what that's done, I think, is it has removed Alzheimer's from having to interact with other neurodegenerative diseases and made it something special when in fact it is probably well integrated with these other diseases. So, for example, vascular dementia. About 70% of the individuals who are diagnosed with Alzheimer's disease, when they are examined carefully, also have vascular dementia as a comorbidity.
Wow.
And indeed, pure Alzheimer's is very, very rare.
Interesting.
So here's the NIH trying to make decisions about funding Alzheimer's when they are not as well organized, I think, as they could be.
Yeah.
And I argue in the last chapters of the book that what really needs to happen is that, and this is complete pie in the sky, but you know, it's my book, so I get to say what I want. But one of the things that needs to happen is Alzheimer's needs to come out of NIA and go back into where I believe it belongs, in the NINDS.
Right. Wow.
anticipating the howls of complaints from my colleagues at the NIA, I argue that what needs to happen along with that is that we need to invest in the biology of aging so that every dollar that comes is lost at NIA needs to be replaced by money to fund the biology of aging. And it may not be sexy or it may not be dramatic, but that biology, that understanding, I think is critical to solving a whole host of human maladies.
That's terrific.
All right, so that's a long-winded answer on the NIA. You want to keep going, or should I
Yes, please.
turn to the regulatory people?
Please keep going. Yeah.
So then how does the FDA start making decisions? Well, I know much less about them. In fact, if I were to critique my own book, I would say one of the chapters that's missing in the book is a chapter on the whole regulatory landscape in which Alzheimer's disease is studied. But they listen to their scientists, and they also listen to the companies whose trial infrastructure comes into interface with them. And ADUHELM is a perfect example of where those two interactions can be in conflict. And then the FDA literally has to make a choice. I guess I would add a third one, which is that there are often, in fact, almost always non-governmental patient advocacy groups, and they also form a pressure point for the FDA. So it's a tough role for them. They need to make sure that a product is safe. They need to make sure it's efficacious, but they also need to respond to the scientific and political pressures that they're under. They have a weighty and important responsibility.
Yep. Great answer. Thank you very much. Really appreciate it. All right. And then we've seen drugs in development positively move maybe one or so. Want to get into start talking about a little bit about cemifalam in cassava here. So we've seen drugs in development positively move one or two biomarkers at a time, maybe. Are there a combination of biomarkers that should be measured or tracked in tandem? And what would be your thoughts about a drug that can positively affect, say, 10 biomarkers after 6 and 12 months of administration?
Right. Good question again. I think, again, I'll come back to what I was saying earlier, was that in each situation, the reliability and validity of the biomarkers is key. So you don't want to put a lot of stock or value on moving a biomarker that has a very tenuous and uncertain relationship to the disease.
Black, yeah.
Okay, you said it. I was thinking it. But having said that, I think the more biomarkers you can have, the better you're going, the more confident you can be that what your compound is doing, it has the potential to be truly efficacious. I happen to be a huge fan of putting the clinical efficacy towards the top of your biomarkers. But as I was saying earlier, in a disease where those clinical markers can take a long, long time to come up, having intermediate steps that are reliable is quite useful. But to your question, the more you have, the better and more confident I think you can be.
Yep. Excellent. Thank you. A great answer. Thank you. And then you stated in your book how not to study a disease. I said in the beginning, your book is called How Not to Investigate a Disease. It's called How Not to Study a Disease. Yours is a better title. You stated in your book how not to study a disease that available now, that biomarkers are far from accurate in diagnosing Alzheimer's disease. For example, 30% of those with plaques show no cognitive impairment, We are very interested in the clinical study results of Cassava Sciences trials, which are showing directional improvements in a full panel of biomarkers of disease in mild to moderate Alzheimer's patients starting from 28 days through 12 months. What are your thoughts on these kind of results? Should we be excited?
Should we be excited? Well, I am excited at the mere fact that this trial is certainly a wonderful example, but I am excited that the field is finally moving off the amyloid dime, and that these other types of studies are finally entering into our trial portfolio and making a difference. Again, I do come back to I really want to see cognition move. And it speaks directly to the way you opened your question, which is that if we don't really understand the biology of Alzheimer's, we can debate the validity of the markers. And that's why I was, strongly in favor of your using anyone using multiple markers as outcome measures. But again, it's certainly my hope that where those are mile markers and steps along the way, before I get excited, I really want to see cognition move.
Yep.
And I come at it as I like to say, a mouse doctor. So we've cured mouse Alzheimer's disease 100 times, and
Yeah.
it's not translated into therapies that have meaning for the human condition.
Yep. Great answer. Thank you very much. Yep. And now, so you are, and now in Cassava's defense, there's also cognition, but they're running large trials now. Yep. So thank you very much. You are working on gene regulation to address the disease. Is it possible that gene dysregulation leads to protein misfolding in Alzheimer's? Can that be a cause of protein misfolding?
Certainly, absolutely. It's the story of aging again. Our everything about our genome changes. So I work on DNA damage and the accumulation of unrepaired damage with age. I work on DNA damage as a trigger for inflammation. When pieces of the fragmented genome get out into the cytoplasm of the wrong cell. So yes, all of that is relevant. Now I've lost my thread, but put the question to me again, if you would.
Protein misfolding. So can that?
Right.
Yep. So like you were saying, it can lead to inflammation. It can lead to a number of things, and then protein misfolding.
Right, but and part of the inflammation story turns out to be a story of lysosomes, and one of the things that lysosomes do is take care of misfolded proteins and get rid of them.
Well, what's a lysosome? What is a lysosome?
So a lysosome is basically the garbage disposal of the cell. You put crap in there that you don't want anymore, and it's a bag full of enzymes that basically breaks that unworkable structure into its component parts, and then recycles the parts because the cell doesn't like to waste anything.
Yep.
So the lysosome really is how you get rid of things that are either objectively bad or beyond their usfulness.
And
they're broken down.
Neurons have lysosomes?
All cells have lysosomes.
Interesting. And then how does that play into gene dysregulation then, the lysosomes?
Well, it plays less into the gene dysregulation, but it does play into the misfolded protein.
Gotcha. Okay.
Because there are two problems with misfolding proteins. The first is you don't want to misfold them to begin with. Yeah. But the second, equally important, is if you do misfold them, you want to be able to get rid of them, and that's where the lysosomes come in.
And then perhaps with age, lysosomes work less effectively?
Yes.
Interesting. Okay. Interesting. Thank you very. So thank you very much. We went off
Sure.
topic there, but that was edifying for me. So thank you very much.
Good.
uh,
As a professor, I'm glad to
yeah,
teach.
right. So Cassava's approach targeting and folding misfolding targeted and fixing misfolded proteins using a small molecule drug, which is a lot more cost effective than a biologic, leading to many potential pathways for fixing Alzheimer's disease. Biomarkers are used for detecting improvements in neurodegeneration, neuroinflammation, and blood-brain barrier integrity. Is this a better or right approach compared to many current antibody Alzheimer's drugs?
Well, I would say compared to the antibody approach, and let's specify amyloid antibodies. I think it's a much better approach. Again, it harkens back to the way clinical trials used to be done and should be done, which is you put a huge premium on efficacy. Biomarkers are a step along the way. They're a tool, but they're not the end goal. The end goal is clinical efficacy. And given that that's how Cassava is approaching the problem, I would say that is exactly right. And we talked before about the use of multiple markers being a much better strategy. So yeah, I think it is a much better approach. Again, I would come back to how difficult these studies are. I mean, and you want to both have short-term goals, but also long-term goals. And the long-term goals are unfortunately expensive when you're talking about clinical trials, but also the ones that are most meaningful. And honestly, and this may be a little off your exact question, but the longer I'm in the field, the more I realize the importance of a very, very simple statement, which is the brain is complicated and its biology is complicated. And one of the things I stress in the book is that the brain is not an island because it exists in a body, and that the health of the body impacts the health of the brain and vice versa.
Yeah.
So, if your heart fails, it doesn't help to have a healthy brain, and vice versa.
Right.
But on top of that, drugs are complicated.
Oh, yeah.
I mean, we design them to do certain things, but often what we discover is that the real power of a drug comes from its multiple forms of action. That yes, it does what we designed it to do, but it also does other things. And for reasons that we may not understand, that's not a negative, that's a positive in my mind. And if we find that, and we're lucky enough to find it, I say we run with it.
Agreed. Yeah, especially in a disease that's always fatal, like Alzheimer's disease, true Alzheimer's disease.
Correct.
Yeah.
Correct.
Thank you.
And there's no overstating how devastating that disease is. I mean, it is one of the worst diseases we can get. I cite in the book a workshop I held with geriatricians. These were not Alzheimer's researchers. They were just geriatric medicine specialists. And at the end of our workshop, because I was trying to figure out, how could we as biologists help that group to, engage in meaningful research. And at the end, I said, look, we've talked about everything from, infections to diabetes to, sarcopenia, what have you. If I gave you a magic wand and told you could fix one thing, what would you fix? And every one of them, even the endocrinologist, said dementia.
Great. Yeah.
And they said that because they said, if you've got a problem with diabetes, I can do something. I can help you regulate your insulin.
Yeah.
If you've got a problem, with a broken bone, I can fix it.
Yeah.
But I can't fix your dementia.
No.
And once you have dementia, all the other problems get worse
Yeah.
because my treatment is now less effective.
Yeah. Wow. Interesting. Thank you. Very interesting. Thank you.
Yeah.
One thing, before I forget, that you were talking about, one thing that I think you do a little bit of research on, you were talking about how the biome or the gut could
Yep.
affects the brain. And I know that, for example, I read that, I was like, and then I thought about this in the gut. The gut is a big part of the immune system, but the gut has regulates serotonin somehow, maybe even more than the brain does somehow. Is no?
We're just learning. I mean, it's another example where I think aging research has been a big push in terms of exploring the importance of the microbiome. But it goes back to what I was saying before, that the brain is not an island. It's, our dementia evolves in a comprehensive biology, and all of it is important.
So I did some quick Googling on that. And so one thing I found that was interesting is that constipation is known to make people angry. and so they were talking about the serotonin system being regulated by the gut. And then, for example, they were saying that constipation is known to make people angry. And that's interesting.
Yeah.
Yep. And then, so lastly here, and then if anybody has, and if you want, we've gone on for almost 45 minutes is what we were scheduled for. So I'll take the last question here. So according to an independent preclinical research by Yale, cassava's semifelam drug has shown to be effective for focal cortical dysplasia, a pharmacoresistant form of epilepsy induced by tuberous sclerosis, another neurodisorder with no safe and effective treatment. The mechanism of action there is also via filament A regulation. Based on your experience, is this strong evidence of an upstream mechanism of action? Do you believe semifelam can be repurposed for such other neurological conditions? Many breakthrough drugs have been repurposed like this before.
Right. So that goes back directly to what I was saying before, which is that not only is our brain biology complicated, but drug actions are complicated. And we design them to do one thing, but they very often will have other effects. I would add to that we often design them to do something specific, say in a neuron, but the protein that we're targeting is also in an astrocyte or an oligodendrocyte or a microglia, other cells in the brain. And the impact of interacting in that cell might be different. So, I mean, it's a long-winded and maybe less than satisfying way to say, I would absolutely explore that avenue. And again, it goes back to the way we used to do medical research, which is we try it, and if it works, we do it again. And I think that should be our gold standard.
Agreed. That's the basis of science, right? There's strictly observation and no speculation. And yeah, great. Well, Dr. Harp, I've learned so much. I really appreciate you making time for us. I'm sure everybody else has as well. There's so many thank yous here in the chat. Do you have time for a question or two from the chat?
Sure, I'd be happy to take a couple questions.
Okay, great. Let's see what we got here. Thank you, Dr. HERRUP. A lot of thank yous here, so thank you very much. Let's see. Some good questions here. We already covered about amyloid evidence for efficacy. This is a good question. So does Dr. HERRUP have any comments on biologic therapies versus small molecule therapies?
Well, let's see, not really. Again, it all comes back to if it works, you do it. But I think where the question is going, and where I think we touched on it in our earlier discussion, a small molecule is almost always easier to deal with. Biologics are expensive to produce and often difficult to administer. And on the other hand, their power is that they can be designed to be incredibly specific. um, and
How do they work?
I don't think there's one answer to that question,
I agree, but
but
that's such a huge. There's so many different biologics and so many different small molecules possible, like there's zillions. Can you tell us? So the biologics, they go the ones that are meant for to get rid of the amyloid. Did they just go and attach, and then then the whole thing is carried off? How do they get rid of amyloid?
well, they get rid of amyloid in a couple of ways. Some of the biologics are meant to block the formation of amyloid to begin with. So they
Right.
inhibit the enzymes known as secretases that cut the amyloid protein out of its larger precursor molecule.
Interesting.
Some of the biologics that have been tried, and this is also true for tau, try to prevent the amyloid peptides from aggregating with each other.
Oh.
And that, according to the amyloid cascade hypothesis, would diminish the toxic effect. So they can work in any number of ways.
I see. Okay, thank you very much. Thank you. And then Mike is a fan of your book. Mike says, very interesting book, Dr. HERRUP. Thank you very much for your time. And then, but he has a question. Given the neighborhood model described in your book, and so this is, and so you're saying instead of focusing on individual neurons, look at them as neighborhoods of neurons to better understand the brain a little bit more and disease a little bit more. Can you hypothesize or speculate how restored filament A improves cognition and normalizes biomarker levels as seen in semifilam clinical trials?
Right. Well, it's a complicated question. Well, it's a simple question, but the answer is complicated. The idea behind the drug is, as best I understand it, is that it's interacting with the actin cytoskeleton to impact how proteins are handled. And my feeling about that from what I know of the field is that we actually need to dig much more deeply into the mechanism, not of the drug so much, but of the interaction between the actin cytoskeleton and things like the synaptic machinery. We think about it a lot, but we tend to ignore what is sometimes the most profound. So actin cytoskeleton is present throughout the cell. It's in every cell. We ignore it, and yet that our cell's shape is governed by that. The flexibility of our cells, mobility of our cells, both in a macro and a micro way, they're all impacted by it. And again, the drug was designed to impact one phase of that, but it's not to say that there aren't, I hate to call them off target because it sounds so diminutive, and I don't mean it in that way, but additional effects of that drug that could very well be important in other situations.
And who knows? It could be that the way that the main method of action is not having the effect at all. It could be that it's an unknown. One of these unknown effects is actually
exactly.
Effect. Yeah.
Exactly.
Yeah.
So we need to dig more into the biology, and I think we should.
Yep. Agreed. So thank you very much. Thank you.
Yep.
And we talked a little bit about this. So I know that you are aware, but someone's asking, Dr. HERRUP, are you aware of the controversies surrounding cassava sciences? And could you say if you believe that they might be justified or not?
I'm aware that there's controversy, but I'll be honest, I have not taken enough time to go into it and to comment effectively.
Would you mind sharing?
Let me just leave it there.
Okay. Then you did compare it to another story. Would you mind sharing that?
No, I wouldn't. And the controversy catches my attention, but it actually doesn't immediately make me run away. And the reason is, and we were talking about this before we came online, there are other examples of sort of, I'll call it unorthodox, but I'm using orthodox in the negative sense of the word. There are unorthodox approaches that are suppressed, and they're suppressed not for good scientific reasons. They're basically trolled, and the facts will come out. And I maintain a completely open mind as to how this is going to work. And I mean, look, the drug is in advanced clinical trials. We will know.
Yep.
We will know.
Yep. Thank you very much. Thank you very much. Very, very fair.
Sure.
And then now we're coming up on an hour here. Let me just see if there are even already more questions we haven't covered. Do you have any more time for us? There is one or two more good scientific questions here.
Go for it.
Thank you very much. So Leon says, Dr. HERRUP, so since tau hyperphosphorylation and fibril formations always accompany amyloid beta 42 aggregation in Alzheimer's, do you have any hypothesis that links these events together?
Well, I'm not exactly sure that's a correct statement. There is still a lot of discussion in the field, and it looks as though you can drive tau aggregation through an amyloid-based mechanism. And while it may be sufficient, it certainly isn't necessary. So there are many other ways, amyloid-independent ways of aggregating tau. And personally, I'm not completely convinced, and I don't think, to be honest, the field is completely convinced either, that even in the very narrow case of pure Alzheimer's disease, pathognomоnically defined Alzheimer's disease, that we are completely certain that amyloid drives the tau.
Yep. Okay. Yeah, it could be that tau is upstream of amyloid. Is that right?
It could be. The example I use in the book is what I call an X factor, where two things are tightly correlated and look like, and we debate whether one causes the other and which way causality goes. But in reality, a very common event in biology is there's a third factor which is related to neither one of them, but it drives both of those conditions. And so that the real driving force is this third factor, not the interaction between the two. So in this case, and again, there's no data, it's just a hypothetical. But rather than thinking tau drives amyloid deposition or amyloid deposition drives tau, there is actually an X factor that drives both amyloid deposition and tau deposition. And they appear to be correlated with each other, which is valid, but they aren't causally related.
Interesting. So they're not causing one is not causing each other. They may be caused by the same thing, but we know that one is not.
Right.
Interesting. Okay. Interesting.
Right. They could be causally related, but I, for one, need more proof.
Thank you. Excellent. Very, very. Thank you very much. And then there was a question about cassava's. Cassava was not only its results on cognition. Someone was saying, how credible is it that I'll just bring it back up. How credible is it that a drug reverses Alzheimer's symptoms? So on the 28 days, there was CANTAB, which is the Cambridge test, and it showed good things. There was only 28 days, but it was placebo controlled. But then at 6 months and at 12 months, and 6, 9, and 12 months, the cognition on ADAS-Cog showed not even a less worsening of cognition, but an improvement, and really an impressive improvement. And then I don't know if you've watched on this channel. We've interviewed a few people now that give firsthand accounts of the improvements of people. So how credible is it that a drug can reverse making not just have the cognition not be as worse, but actually get better? How credible is that?
So, wow. I know that sounds like a simple question, but it's a complicated answer again.
Okay.
Let me start with the mice. This may sound like a detour, but I don't think it is. So when I say we cured mice Alzheimer's many, many times, we have. We can get rid of plaques in the mouse brain. And when we do that, their behavioral symptoms improve.
Okay.
Now, the problem I have is that I'm not sure how relevant those behavioral symptoms are to what we call Alzheimer's disease.
Right.
So could a drug like simufilam improve cognition? Of course it could. It could be acting in the same way that it's acting in the mouse.
Yep.
And yet the underlying biology of Alzheimer's disease might still be progressing.
Yep. Yep.
So that would be a very complicated curve.
Yeah. Yes, it would.
Is that a valuable therapy? Oh, absolutely.
Especially there's not much out there.
Oh, yes.
Yeah.
Because you're dealing with a disease of age. And I'm sorry to be so cold about it, but we will all die of something. And really our goal is to keep as my geriatrician workshop pointed out, we want to keep our cognition as intact as possible, as long as possible. But theoretically, you can't get better from Alzheimer's. You can only stop getting worse.
Gotcha.
And for my money, that's the disease I'm trying to study as a basic scientist. So I believe that a drug could, in fact, improve cognition, but I think it's doing it by mechanisms that aren't related directly to the Alzheimer's disease problem. Is it a valuable drug? Yes. Is it stopping the progression of Alzheimer's? Maybe not.
Okay. Fair enough. Well, fair enough. Thank you very much. I appreciate that. Thank you. And then Zeus Zhang says, and then we're coming up on an hour. Let's make this, there's this and then one more question if you have it in you.
I got it.
All right. How about defects in protein translation and integrated stress response and Alzheimer's? Defects in protein translation and integrated stress response in Alzheimer's.
I could absolutely put that on my list of possible causes and things worth working on. My quick response, but it's something we could discuss, is that those issues are much more related to just general aging. Now, as I said before, that impacts Alzheimer's disease, it affects Alzheimer's disease, but my guess is that the processes you're talking about are not specific to Alzheimer's disease, but probably relate to a variety of diseases of aging.
Okay.
Again, usually relevant, but not specific.
Okay. Excellent. Thank you. And then lastly here by Keith Salcorn, who gave us a good question earlier, there are enhanced intellectual property protections for biologics as compared to small molecules, 12 years versus 5 years of FDA exclusivity. Does Dr. Harp believe preference is appropriate? And I'll add to that as well, biologics are also preferable by investors, basically, because the generics can't come along and use the data from the big companies' biologics, because when you bring a biologic along, it's created like in a cell culture, and one lab doing it is different than another. Whereas a small molecule is synthesized, so a generic can use the data from another company and not run all these trials on a generic, but it must run all these trials on the biologics. There's another reason as well. But this question is about, and also on top of that, the FDA gives special enhanced intellectual property protections. Do you feel that is appropriate, is the question.
Whoa, boy. So what I say in the book, and I try and hammer this point home, is that it's easy to think of the pharmaceutical companies at every level as villains in this story. And yet, as I point out, there is no way that we will ever come up with a cure, a meaningful cure for Alzheimer's without them.
Yes. Yep.
We need their production capacity. We need their testing. We need their distribution. So in many ways, the fine points of whether a biologic is worth more patent protection than a small molecule, I think we're at the I don't want to say this, we're at the edges of the problem that concern me about the pharmaceutical industry. I think that the defects in their regulation and in their behavior are much deeper and much more profound than whether they get a few more years for one type of medicine over another. I realize that's not addressing the question the way you wanted me to address it, but after all the time I've spent writing the book, this is sort of where I come down.
Okay, very fair, very fair. Thank you. And if I can ask you one more, I'm sorry, but to get back to when you gave an excellent answer about the nature of perhaps in Alzheimer's specifically that you couldn't the disease that you could perhaps halt the progression, but reversing it would be a different question. And a very fair answer you gave. I did want to point out that there was a study that I wrote about that looked at small molecules targeting misfolded proteins, and in all the drugs that were studied for like long periods of time, 2 or 2.5 years or even longer, all of them showed an increasing benefit over time, and all the way out to 2.5 years. As long as they kept studying, it kept getting better. Because it's possible the nature of protein misfolding diseases is actually reversible in something of a metaphor to making the structure more and more sound over time. It is of the filament and making the structure of the filament more and more sound over time. Is that reasonable or not reasonable?
Yeah, I mean, sure, it's most reasonable, and I hope neither you nor your listeners are confused. I'm trying to make a very specific case that the degenerative process of Alzheimer's, the biology behind that, might be different than the biology behind improving misfolding proteins that allows constant improvement. It doesn't mean that you're not doing something really important for Alzheimer's disease, because Alzheimer's is the sum of the normal aging process plus the Alzheimer dementia process. And attacking either one of them is hugely valuable for our assault on Alzheimer's.
So it's possible we can keep seeing it out for a few improvement after a few years, because it's yep. something along the lines of improving aging, where and
correct,
the Alzheimer's symptoms are all getting better, but you've actually improved aging. So would that then, could it possibly be improving other diseases of aging and not just Alzheimer's?
That would be my guess, absolutely. Because again, if you're improving aging, and I like to call it uncoupling aging from the degenerative processes that assault the brain, you're having a big impact, and not just on Alzheimer's, but on other diseases as well.
So this is very interesting. So this is possibly an anti-aging drug, not an anti-Alzheimer's drug.
Well, I'm not. Yeah, and that may be a distinction without a difference. So,
or interesting. Okay, a distinction without a difference. Thank you. Interesting. Wow. Well, it's been more than an hour now, Dr. Harp, and I've learned so much speaking with you. I've had so much fun speaking with you off camera as well. So,
great.
Off YouTube as well. So, so many thank yous coming in from the chat. I can't say thank you enough for making time to come and speak with us. Your book, How Not to Study a Disease, is available now on Amazon, and where else?
It's available directly from MIT Press, who's the publisher. It's available on all the typical online reading sources. So Yeah, please read. Let me know how you think about it.
And do you have a, you know, I went to your website, but it's down. I guess you don't do your website anymore.
Yeah,
But yeah. So do you have anything else
I'm
that you
not
plug?
real good about my website.
Well, you are good about your Twitter, though. Do you want to plug your Twitter?
I am active on Twitter. Yes, I am.
Well, that is so. And what are your? What was your doctor? I can't remember. What's your Twitter handle?
It's at KARL HERRUP.
At Karl Harp. So that's brilliant that you got that. And then yeah, the websites are, nobody cares about websites. You don't need your website. You're on the platform like Twitter. That's where you need to do. So perfect. So great. So buy the book and follow him on Twitter. Dr. Karl Harp. Thanks so much for making time for us today. So many thank yous coming in here.
Great, my pleasure.
Thanks so much, everybody. Thanks so much for joining us on Alzheimer's, and we'll end it there. Thanks very much.